let's put our pressure and force thinking to work. Here's an aquarium display, probably some famous aquarium. So you would hope that the people who designed this accounted for the total force of the water on the big piece of glass here. So how much force are we talking about there? So let's go compute that. So let's draw a diagram of that problem. The surface of the water wasn't even visible in that picture. It's got to be maybe a meter above the top of that window. So we'll have a window here. And from the surface of the water to the top of the window, let's just guess that that's something like a meter. And we don't know the exact direct dimensions. Let's say 2.5 meters tall and 3 meters wide. And we want to compute the total force on the glass. Well, can we just use force equals pressure times area? Well, if the pressure was the same across this whole area, then sure, we could. But the pressure is less up at the top than it is at the bottom. So we can't use this all in one application. We need to think about what's going on here. The pressure on the glass is different at different depths. So what do we do in calculus when there's something that's different in different locations, but it sure would be nice if it was constant? We treat it in thin slices, and where each slice is approximately constant, right? So we're going to slice it up. So the pressure on each slice is approximately constant. So what does that mean about slicing this up geometrically? Am I going to slice it up vertically, horizontally, in little grid squares? What do you think? Well, at any one depth, the pressure is roughly constant. So I could say I'm going to slice this up with a little slice here, because everything in that slice is at the same depth. What would you say is the thickness of that slice? That might be kind of important. Well, we want it to be thin, and it's in the y direction, so we might call it dy, right? What's the depth of that slice? Maybe we'll have a scale along the side here that says 0 meters, 1 meter, and down here, what's the total depth of that slice? That'd be 3.5 meters, because we had the 1 meter here and then 2.5 meters there. So we can call those y amounts. It's not typical to have y increasing as we move farther down, but mathematically there's no reason not to. So what's the pressure on that bottom slice? Well, remember the formula for pressure is rho times g times depth. We know rho, we know g. What's the depth of that bottom slice? 3.5 meters. What's the force on that slice? Well, force is equal to pressure times area. Pressure we know was rho times g times 3.5. And what was the area? Well, we hadn't computed that. What's the area of that slice? Well, its width is 3 meters. So we could say its width times its height. Its width is 3 meters and its height is dy. So that's for the bottom slice. What about the next slice up? Well, you still have rho times g times, but now instead of 3.5, what's the depth of that next slice up? It'd be something smaller, like 3.49-ish, maybe, times what's its width, still 3 meters, times its thickness, which would be dy, or its height. So then we add it all up. So how are we going to add up all those slices? Well, we could set up a spreadsheet, and there we'd have to choose a dy value, like a centimeter or a tenth of a centimeter or something. But in by hand calculus terms, we're going to do an integral. And where does our y value start and stop? Well, we know our biggest y value was 3.5 meters. What was our smallest y value? Starting at the top of the aquarium window here, so 1 meter. So starting at 1 meter going to 3.5 meters, rho times g times depth, but depth is now y, times a width of 3 meters times dy. Is that going to be a fairly simple integral to do? Rho and g and 3 are all multiplying constants. You can just leave them there, or you can move them out front. So it's basically the integral of y dy, which is something you've probably been doing for a long time now, right? Someone asked me when I taught this face-to-face, can we actually do this integral all the way out? So sure, why not? I'll do that in a later video. Now, I just kind of chose the depth system here. Someone once said, well, why do I have to put 0 meters up here? If I wanted y to increase as I move upward, couldn't I use y equals 0 here? And then what would y be here? Well, the window's 2.5 meters tall, so I could put 2.5 there, and then I could have 3.5 up here. Would that work? So think about, can you formulate the integral to use this system of measurement rather than that system of measurement? Well, it turns out okay. So where would you start integrating here, and where would you stop? I'd go from 0 to 2.5. And rho is still the same, g is still the same, but remember this y, that was the depth. So let's just write d for now. The width of the area was 3 meters, and then dy is going to stay the same. But what is the depth now? If I tell you I'm at y equals 0, I'm at depth 3.5. If I tell you I'm at y equals 2.5, I'm at depth 1 meter. So how can I translate a y value in this system to a depth? You notice in each case it adds up to 3.5. So this y value plus the depth would equal 3.5. So I could replace the d here with 3.5 minus y. It's basically a u substitution, right? We're just changing this variable from y to 3.5 minus y. du would just have a minus 1 dx or something, minus 1 dy, and we would change the limits. And does it look like when we change the limits from y to u or vice versa, you would basically get this translation? Yep, it all works. So in this case, we were lucky because the window had constant width. So in the next video, we'll talk about what if the window is not rectangular.